In example 4, we need to solve each equation for the variable indicated. If we need to, we'll round to the nearest thousandth. Looking at this part A here, the first one, we've got log base 3 of something, log base 3 of another thing, log base 3. All the bases are the same. And we have 2 logs on one side, 1 log on the right, with no other numbers that are outside the logarithms. The technique to use here is to try to combine these 2 logarithms together. Then we're going to have a log with base 3 on one side and a log with base 3 on the other. We can then set the argument positions equal to each other. So remember that when we're adding logarithms, we're actually multiplying these parts together if we want to combine those or condense them into one logarithm. So this is going to be x minus 6 and then times 2, and that's all in this argument position here. We'll have log base 3 of 5 on the right side still. Now we can take this entire part right here and set it equal to this entire part. When you have 1 log on one side with the same base as the other side, and there's only 1 log on the right side, you're allowed to do that. So this is 2x minus 12, if we do the distributive property, is equal to 5. We need to add 12, making 2x equal to 17. Divide by 2, and x will be 17 over 2, or you can list the decimal or a mixed number equivalent as well. We need to make sure that this makes sense though for our original equation. There's only one thing we need to look at here, and that x minus 6 needs to be greater than 0. X must be greater than 6 then, if we add 6 to each side. 17 over 2, if you find the decimal equivalent, that would be 8.5, and so x, or 17 over 2, or 8.5, is definitely greater than 6. So this is a good, valid answer. If we work with B, you'll notice that in this case there's 2 logarithms on the left-hand side with the same base, but there isn't one on the right-hand side. So we're going to have to use a little bit of different technique than we did for A. What we'll do here is we'll try to combine these or condense them into one, and then we'll have a logarithm on one side and a number on the other. Then you know it's time to change that into an exponential. So we have log base 3 of y minus 9, and then we're adding logarithms, so we're going to multiply the argument positions, and that's going to be equal to 5. If we go ahead and FOIL this out, or perhaps you might notice that this is a difference of 2 squares. So we're going to write this as 3 to the 5th power is equal to y squared minus 81. Again, if you want to, you can FOIL this out. You're going to find it's y squared minus 81, a difference of 2 squares. 3 to the 5th power. Well, that would be 3 times 3, which is 9, times 3, which is 27, times 3, which is 81, times 3. That should be 243. That's equal to y squared minus 81. We can add 81 to each side. So this is going to be 324 is equal to y squared. We can square root each side, or if you prefer, you can raise that to the 1/2 power. That's not one that I recognize, so I'll have to do this in the calculator. 324, oops, don't need a sign there, and that's 18. Could be both positive or negative 18. We need to go back and look and see what values will work. So both y minus 9 and y plus 9 have to be greater than 0. If we add 9 to each side, we'll have y is greater than 9. If we subtract 9, y is greater than negative 9. This one's the more restrictive one, so we don't even need to pay attention to this one. Any number that's greater than 9 is already greater than negative 9. In selecting our answer, we need only the positive value here. So you have to at least entertain the fact that it might be both positive or negative, but then go back and look. And a negative 18 would make this position negative, and that's no good. We can't raise 3 to any power, no matter what you pick, and get you a negative value. So we have to disregard or throw out negative 18 as an answer, even though it's possible. Really 18 is the only one that will work.